Good morning again. Today we're going to be talking about momentum. We're going to be looking at sections 8.3 and 8.4 today. So remember, momentum is conserved for all collisions as long as external forces don't interfere. The concept of inertia was introduced and developed both in terms of objects at rest and objects in motion. In this chapter, we are concerned only with the concept of inertia in motion, or momentum. So let's talk about something that bounces. The impulse required to bring an object to a stop and then throw it back again is greater than the impulse required merely to bring the object to a stop. Suppose you catch a falling pot with your hands. You provide an impulse to reduce its momentum to zero. If you throw the pot upward again, you have to provide an additional impulse. If the flower pot falls from a shelf onto your head, you may be in trouble. If it bounces from your head, you may be in more serious trouble because impulses are greater when an object bounces. The increased impulse is supplied by your head if the pot bounces. So remember back to yesterday. If a flower pot dropped onto your head bounces quickly, that's going to hurt. If bouncing took a longer time, as with a safety net, then the force of the bounce would be smaller. Here, a student imparts a large impulse to the bricks in a short time and produces considerable force. Her hand bounces back, yielding as much as twice the impulse to the bricks. Here you can see a block topples when a swinging dart bounces from it. With a rubber head of a dart, it doesn't bounce when it hits the block and no toppling occurs. Another instance is the water wheels used in gold mining. Lester Pelton designed a curve-shaped paddle that caused the incoming water to make a U-turn upon impact. The water bounced, increasing the impulse exerted on the water wheel. The curved blades of the Pelton wheel cause water to bounce and make a U-turn, producing a large impulse that actually turns the wheel. In your notes, go ahead and write down, how does the impulse of a bounce compare to stopping only? In section 8.4, we're going to be looking at the conservation of momentum. The law of conservation of momentum states that in the absence of an external force, the momentum of a system remains unchanged. The force or impulse that changes momentum must be exerted on the object by something outside the object. Remember yesterday we looked at internal forces in the soccer ball and the car and found that they did not actually cause something to move. Molecular forces within a basketball have no effect on the momentum of the basketball. A push against the dashboard from inside the car does not affect the momentum of a car, because these are internal forces. They come in balanced pairs that cancel within the object. Let's take a look at our cannon again. The momentum before firing is 0. After firing, the net momentum is still 0, because the momentum of the cannon is equal and opposite to the momentum of the cannonball. The cannonball's momentum is in speed. The recoiling cannon's momentum is in mass. So here we have two things that are the same because the momentums must be the same. But m times a larger v is equal to larger m times a smaller v. The force on the cannonball inside the cannon barrel is equal and opposite to the force causing the cannon to recoil. The action and reaction forces are internal to the system, so they don't change the momentum of the cannonball system. Before firing, the momentum is 0. After firing, the net momentum is still 0. Net momentum is neither gained nor lost. Momentum has both direction and magnitude. It is a vector quantity. Remember, momentum, p, depends on mv. Velocity is also a vector, and so momentum must also be a vector. The cannonball gains momentum and the recoiling cannon gains momentum in the opposite direction. The cannon-cannonball system gains none. The momenta of the cannonball and the cannon are equal in magnitude and opposite in direction. No net force acts on the system, so there is no net impulse on the system, and there is no net change in the momentum. In every case, the momentum of a system cannot change unless it is acted on by external forces. When any quantity in physics does not change, we say it is conserved. A conservation law is constancy during change. Conservation laws are a source of deep insight into the simple regularity of nature and are often considered the most fundamental of physical laws. The law of conservation of momentum describes the momentum of a system. If a system undergoes change, wherein all forces are internal, the net momentum of the system before and after the event is the same. Some examples: atomic nuclei undergoing radioactive decay, cars colliding, and stars exploding. Newton's second law states if no net force is exerted on a system, no acceleration occurs. Does it follow that no change in momentum also occurs? Go ahead and summarize. What does the law of conservation of momentum state?